Section 4.3, Graphing Functions. In 4.3, you were given this graphing guidelines for a function f of x, and I'm going to do an example for you that follows these guidelines. It may not be in exactly the same order, but I'm going to go through most of these steps here. So, some of the guidelines are you want to look at your interval of interest or identify the domain. You want to exploit symmetry, so is the function even or odd? You want to take the first and the second derivatives. So the first derivative can tell you where critical points are, where the function is increasing or decreasing. The second derivative can tell you the concavity, so the curvature of the graph, which will be helpful when you're trying to sketch it. Then you want to find critical points and inflection points. Again, critical points are where the first derivative is 0 or undefined. Inflection points are where the second derivative is 0 or undefined. Then we want to look for, well, I kind of already said that, intervals of increasing, decreasing, the concavity. We want to look for the extreme values. We want to look for asymptotes. We want to look at the end behavior. So the end behavior is when x is going to plus or minus infinity. And then we want to look at the intercepts, x and y intercepts. Those will also help us to graph a function. Okay, so you probably went over graphing functions in pre-calculus or college algebra, but now we have a few more tools to help us get a better graph. Let's see this example. So here I have a rational function. We're going to graph this rational function with both pre-calculus and calculus concepts now. So first let's talk about the domain. So the domain are all the valid inputs. We've got 3x over x squared minus 1. So the domain is going to exclude any points that make the denominator 0, which are plus or minus 1. So x can't equal plus or minus 1. So our domain is minus infinity to minus 1, union minus 1 to 1, union 1 to infinity. While I'm at it, might as well identify if we've got vertical asymptotes or not. So if you recall, vertical asymptotes occur when the denominator is 0 and there's not a shared term between the numerator and denominator. So the vertical asymptotes are going to be a plus or minus 1. We've got a horizontal asymptote. So the horizontal asymptote is y equal to 0. And we can prove that by dividing out every term by x squared. So we'd have 3 over x over 1 minus 1 over x squared. A horizontal asymptote is what the graph does at infinity. So as x gets very, very, very large and positive or very, very small and negative, we're going to approach 0 over 1, which is 0. Okay, so that justifies our horizontal asymptote here. Okay, let's look for the x and the y-intercept. So the x-intercept is found by setting the function equal to 0. Okay, so where is the function 0? Well, it's going to be 0 when the numerator is 0, which is at 0. Okay, so the x-intercept is the point 0, 0. The y-intercept is found by setting x equal to 0. Okay, so if we set x equal to 0, we've got y equal to 0 over 0 minus 1, which is 0. Okay, so the x and the y-intercept are the same point here. It doesn't always happen, but it did in this scenario. Alright, so we have found some very key things about our graph. If this were pre-calculus, we would probably start sketching at this point. But we are going to identify some additional details. So let's find the first derivative. F prime of x equals. Okay, so we've got a quotient So we've got the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Okay, in the essence of time, I'm just going to simplify this for you. If you simplify this all out and multiply the numerator out, cancel any terms, combine any terms you might have, you can simplify it down to minus 3 over x squared minus 1. Okay, so you might want to pause the video and verify that, but that is what the first derivative simplifies down to. And let's go ahead and find the second derivative. So f double prime of x, again we use the quotient rule, denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. And that simplifies to 6x over x squared minus 1 squared. Alright, so critical points. Well, we actually don't have any spots where the first derivative is 0. Again, the first derivative is this minus 3 over x squared minus 1. That's never equal to 0, but it is going to be undefined at x equals plus or minus 1. So for critical points, we'll just say undefined at x equal to plus or minus 1. We already really categorized what's happening there. It's there's vertical asymptotes at those locations. Okay. Inflection points are where the second derivative is 0 or undefined. So the second derivative is 0 at 0. Okay, so here's our second derivative. That's going to equal 0 when x is 0. So there's an inflection point at 0. We also want to check the concavity before and after plus and minus 1, because the concavity could change on the left or the right of a vertical asymptote. So I'm going to just write a note to self, check around x equal to plus or minus 1 as well. Okay, so now let's look for the intervals of increase or decrease. Okay, so let's see here. I want to check around the asymptotes. Okay, so ideally I'm looking for critical points here, but again we don't really have any points where the derivative is 0, we just have points where it's undefined. So I'm looking at f prime of a test point. I'm going to pick negative 2. And I'm looking in the interval minus infinity to minus 1. Then I want to look at the value of the first derivative between minus 1 and 1. So I'll test f prime of 0. And then I want to look at the interval from 1 to infinity, so I will test f prime of 2. So f prime of negative 2 gives us a negative number if we plug everything in. F prime of 0 gives us a positive number. And f prime of 2 gives us a negative number. So it tells us that f is decreasing on minus infinity to minus 1 and from 1 to infinity, and it's increasing from minus 1 to 1. Alright. Next I want to look at the concavity. So I'm going to look at concavity. So I'm going to look around the vertical asymptotes around 0. So I'm going to test the concavity on the interval from minus infinity to minus 1. I'm going to look at the concavity from -1 to 0. So my test point, I'll pick -1/2. Oops. Then I want to test the concavity from 0 to 1, so I'll test f double prime of 1/2. And lastly, I want to check the concavity from 1 to infinity, so I'll check f double prime of 2. Okay, so I'm going to stop this video. I'm going to have to make a two-part video here because I'm getting up to the upper time limit for this video. So I will be right back with this.